This is a very important playlist, RNN with stack. And my motivation comes from many different things, such as neuroscience, such as computation theory. Everything about finite state machines, stack, data structures, and Turing machine, and many things. Language, context-free grammar, formal language theory. So you see, everything can be used to create new methods for RNN. So future of RNN is much more complex than what we see today. And I want to focus on this important article in 2015. And these are positive samples. It means that they are related to this article. There are similar ideas. So the idea is that stack algorithms are well suited to processing the hierarchical structures observing in natural language, and we hypothesize that their neural analogs will provide an effective and learnable transduction tool. Our models provide a middle ground between simple RNNs, a recently proposed neural Turing machine, and I've explained this in one of my playlists, which implements a powerful random access memory with read and write operations. I have a playlist for sparse distributed memory as well. Neural stacks, queues, and dequeues are also provided a logically unbounded memory while permitting efficient constant time push and pop operations. So your neural stack is a little bit, so let me show the architecture. So neural stack is a differentiable structure onto and from which continuous vectors are pushed and popped. So inspired by neural push-down automaton, push-down automation is kind of finite state machine, but the transition, just like DNA in your body, the transition depends on some stack. So it's non-deterministic, but it has limited diversity. So we render these traditional discrete operations continuous by letting push and pop operations be real values in this interval. Intuitively, we can interpret these values as the degree of certainty with which some controller wishes to push a vector onto the stack or pop the top of the stack. So this is the stack. So these are the elements. So a stack at time t is a vector. So when any of them, for example, this element is called st of I because that is the ith element of this stack. And this is what you read from that. For example, a combination of our vectors. So a neural stack fully parameterized by embedding size is described as some time step at time step t. So it's a t by m value matrix, t by m. Because at time t, we have a t by m matrix. So at time t, we know this is for time t. This is for time t plus 1, t for t minus 1. And this is the definition of vector, but this is the important dynamics of your stack. Your stack at time t uses the information for stack at time t minus 1, and is updated like this equation. And what you read, your read operation, is this dynamics, which are similar to the pop operation. And a fixed read quantity of 1 is set at top of temporary copy of this transvector S sub t, which is traversed from highest index to the lowest. If the next strength scalar is smaller than the remaining read quantity, its value is preserved for its operation and subtracted from the remaining read quantity. If not, it is temporarily set to remaining read quantity, and the strength scalars of all lower indices are temporarily set to 0. The output R sub t of the read operation is the weighted sum of the rows of V sub t scaled by the temporary scalar values created during the traversal. So an example of the stack read calculations across 3 time steps after pushes and pops is in this figure 1a. For example, read sometimes becomes at time step 2, it becomes a linear combination of V1 and V2, and in time step 3, you see it's a linear combination of V1, V2, and V3. Now, this means when it is 0, when the value is 0, it means that V2 is removed from stack. So this is how your stack grows upwards. And at different time steps, you have different, your vector changes. From nothing, from V1 changes at the next time step becomes V1, V2 and nothing. At the next time step, it becomes V1, V2, and V3. And so we get inputs from previous state and input, but you separate them. Is the opposite of concatenation. You divide them into 3 different things. Just like how you concatenate it, it's just the opposite of that. So some of them are used for push, some of them your pop strength, and some is value. And the next state is a combination of next strength and your values. So whenever you see this, it means that we are splitting. We are splitting at the source, but we are joining at the output because we want to join or concatenate the next value with the next strength so that at the next step understands us, so that it is the next step, so it comes for it will be used for a next state. And we also have some output. So it's a kind of generalization of recurrent neural networks. Or you can replace your RNN with LSTM, by LSTM, GRU, by GRU, or any other versions of recurrent neural networks. But the important thing is if you augment it with this neural stack, or in future advanced things, we will replace it by more complex stuff, like push-down automaton that has a stack as well, and it's just the DNA strands in your body. It's like a push-down automaton, and it's just works on these codes, and depending on transition, we go to a different states, and depending on the next thing, something happens. So it's like I don't say Turing machine because it's more complex than Turing machine, but the DNA inside your body has. So all of these are motivations for you to study DNA computing and those important things. So our neural queue operates the same way as neural stack, with the exception that the pop operation reads just the lowest index of the strength rather than the highest. This is just this small difference. So your stack is updated like this, and what you read is just a linear combination of your vectors. So its neural DQ is it's like both sides. You can insert at the front and remove from front, but at the same time you can insert at the rear and remove from the back of that. And this is the idea that they have created another version of that has top and bottom, just like this one, that has top and bottom, because you can read from any side. You can do some work on any side of that. So this is a generalization of that. It is called neural DQ. And so we can have interaction with controller. While three memory modules described can be seen as recurrent layers, with the operations being used to produce the next state and output from the input and previous state being fully differentiable, they contain no tunable parameters to optimize during training. As such, they need to be attached to a controller in order to be used for any practical purposes. In exchange, they offer an extensible memory, the logical size of which is unbounded and decoupled from both the nature and parameters of the controller. And from the size of the problem they are applied to. And here we describe how any recurrent neural network controller may be enhanced by either neural stack Q or DQ. And here in figure 1C here, we wish to replicate the overall interface of a recurrent layer as seen from the outside. The dotted lines, which takes the previous recurrent state and output vector I sub t and transforms them to return the next current state. So this is the next one, then the next one. And so it's a recurrent neural network, so it's a generalization of RNN. But you have push and pop scalars. This is for push and this is for pop, that the overall input is concatenated with the previous R sub t minus 1 and passed to the RNN controller as input along with the previous controller state. So our output is not only a combination of, but our output is a little bit different. So this is the interaction with the controller. The only additional trainable parameters in either configuration relative to non-enhanced RNN are the projections for the input concatenated with previous rate into RNN controller and the projections from the controller output to various stack or queue inputs.